going to talk about today is about state feedback. Okay, so essentially this is the very important control design class. That means knowledge when you design a controller, you may ask whether it's a state feedback or output feedback. State feedback means that the state of the system is available to you, and that's indeed contains a lot of information. So once you have a state feedback, then in that case, normally you could then do several steps. The first one is to assess what's the so-called, we call it achievable performance. So that's mean the best performance I can achieve, given that I'm fully aware of what's going on inside the system, because state is related how in the internal variable system or how system property are propagated internally over time. So once you explore state information, that means you begin much understand what's going on within the system. And then if you try to design a controller, definitely you would hope that I can design a controller in the sense of optimality. That means achieve certain performance. And this is kind of performance that we call achievable performance, because later on you will then realize that in certain cases state is not available to you. That means you can only measure certain variable, but not all the state of the system. In that case, you will then ask another question: how good am I in estimating the state? So that's essentially the approach modern control, including optimal and robust control, have been using. You try to ask yourself a question, say suppose state, or we call it full information feedback, what I can do. And then afterward, then what if I only have partial information or output feedback? Can I do the performance up to which extent? So essentially, that's a strategy that we have been using. So if you look at the design problem, if you look at this equation and the previous equation, you will realize that the state derivative equation or state differential equation are the same. So x is the state, u is the input, w is the exogenous input. So u is the control input, so the control signal you try to synthesize. W is the external, for example, disturbance, noise, and so forth. And z is the variable you want to monitor. So you want to monitor this variable, so that's maybe this variable is bounded in certain sense. The difference between this equation and previous one is here. That means in the previous one we have y equal to, for example, c0x plus d0u plus d01w. But now we assume state is fully available. So this we call it a standard state feedback information. Or sometimes we call it full information system. That means y not only x and then also w is available to it, but typically w is external to the system, so that's sometimes can be measured, but in many cases that's we call it full information. That means suppose I have all the information and you ask yourself the question how good I can do in terms of the control. And the control law or the feedback control system we will be looking at or will be more interested in what we call state feedback. So that means I have the state, so I just multiply by a state feedback matrix F, and then that's turned out to be my control signal. And you could realize this is a very simple control because you only need proportional control. That means you only have a state, and then you just multiply by a certain gain matrix to control the control signal. So this controller is relatively easy to implement because if I have a state in the computer, just multiply by a matrix, and then let's give you the control signal. So this easy implementable and the main clear control option. And then we'd like to use this operation to look at how if I induce this controller to this system, then how the performance will like. And then if we combine this equation and that equation, then we can realize a closed loop map. That means the closed loop transfer function from w to z can then be expressed as follows. So that means you just substitute u equal to fx here and there. So you end up this kind of description. So let's give you the closed loop map. And definitely if you want to ask how good this state feedback control is, then you will then evaluate this closed loop map. evaluate what? Evaluate internal stability, performance, and robustness. And so far we already know how to evaluate stability that relates to A plus B 0F. We also know how to evaluate the performance as well as the robustness. So we will see how this thing comes out. But the most important observation is as follows. This is the beauty of this theory. That means, suppose I'm looking at stability. So typical stability is for A plus B 0F to be stable. So you could then evaluate, for example, the eigenvalue of the metric A plus B 0F. But definitely you could do something else. And one result that we have been obtained is as follows. So the matrix A plus B 0F is stable if you can find a positive definite matrix X. So that's this term is less than 0. So that means this term is negative definite. This result we already know that. Or sometimes we can then, for example, this closed room plus a positive definite matrix equal to 0. And then that's essentially give the same similar result. So that's a result that we already know. But sometimes we will ask for more. That means sometimes in addition to stability, we will ask for some additional performance or robustness. One of the performance that will be interesting in the for this closed room map is for the H2 norm from W to Z to be bounded. And if we look at the H2 norm, it's related to, there are two methods so far we know how to evaluate the H2 norm. One is through the diagonal equation. That means by solving the controllability or observability gradient, and then you could then obtain the two norm. So the two norm, one way to do is the two norm is equal to the square root of trace B1 transpose X B1, and X is the observability gradient, okay, which solves this equation. And also you could then resort to the, for example, controllability gradient, and you could then similar formulation. Definitely, there are another way to evaluate two norms to LFI. But in any case, if I evaluate the observability gradient, I end up this. So once I solve the observability gradient, then I could then evaluate the two norms. But the nice thing is, if you compare this particular equation for stability and this particular performance, you will realize that suppose I impose certain constraint of performance, then that's automatically guarantee stability. Okay, so that means suppose I have a design that could realize this equation, then that's automatic guarantee stability. So you could then think about the requirement for performance definitely is more stringent or than the stability requirement. Okay? And the difference lies in here. Okay? Or in that case, if I select a particular term for this Q and then I end up this equation. And also we could then consider these two equations. So now suppose you thinking about the design. Suppose you are the designer. Okay. As a designer, you are given this A, B, C, D's. Okay. And you are supposed to find this F because that's a static backend. And you hope that you can find a particular F so that's the closed loop map enjoys certain property. So F is something to be determined, or the metric to be determined. And it's saying that the determination of F is coupled with this particular equation. So this equation plays a very important role in revealing the performance and stability and later on robustness of the system. But if you examine this equation more closely, you will see certain coupling between unknown because A, B, C, D as we know is known. So F is not is to be determined. And same thing X, because you do not know X either. Okay? So for this equation, there are two unknown. One is F and another X. And there are two constraints. One is this term to be less than 0. Another constraint is X had to be positive definite. So that's it. So you are subject to certain equation to be satisfied and certain free variables. If you including x and f. And if you look at the performance, that means if you want to H2 norm to be as minimum as possible, and that's related to this one. In that case, you have to solve this equation. And this particular equation contains also x and f as unknown. But you will see certain coupling here, that means there's f transpose f in this term. So the equation appears to be a little bit more complicated. So here we see the coupling between x and f. And here, the coupling remains there, but we also have f transpose f because f is unknown, so this is another a little bit complicated than this one. So you will then expect a solution for performance, and definitely is more stringent or more than the stability requirement. If we go one step ahead to look at the so-called robustness, and one way to look at the robustness through, for example, small gain theorem. And since small gain theorem, we know that suppose I could bound the infinity norm of n, then I would then understand how much I could tolerate for uncertainty. So if you look at it from that perspective, you will hope that the infinity norm on W to Z to be bounded by certain variable, in this case could be gamma, and the equation that you need to be addressed for you as follows. And this is the equation that we have been talking about when we talk about the H infinity evaluation. That's essentially the equation that we have to solve for closed loop system. But if you look at this equation in comparison with the stability and performance, you see that this equation is one step ahead than this equation, because if you this equation there, then you put something here. Okay. So when you put something here, that's make this equation more stringent. Okay. As this equation is more stringent than this equation. So you could then think the requirement of robustness is more stringent than performance, and it's more than the requirement for stability. So we are, have a 3-step in realizing our control to that strategy. And also in this particular equation, there's a gamma there. So the gamma can play certain role in this equation. And as you could imagine, suppose I allow gamma to go to infinity. So that means if I relax this H infinity norm criteria, that means I don't care about what the infinity norm is. I make it equal to infinity, because there's the inverse there. So this term will become negligible or close to 0. In that case, this requirement is the same as this one. Okay, so that means, so you could think about the robustness requirement. If you relax the requirement to allow gamma to be infinity, then you recover the H2 performance. Okay, so you could see the similarity there. So with this kind of understanding, then we'll go to look at this equation, and then this equation, and finally to this equation, and then see how can you solve F based on this kind of requirement. So first of all, we'll take a look at the so-called quadratic stabilization. So it's a way to stabilize the system, but the quadratic stabilization is a special class of stabilization technique. And the key concept is as follows. So you construct a quadratic diagonal function to govern the stability of a closed system. If you remove this word, that means if you remove this quadratic, that means construct a diagonal function to guarantee. That's typical stabilization problem. So, for example, you want to ensure stability, then you just ask, is there exists a diagonal function that can provide this kind of stability guarantee? That means it can ensure stability. But now, suppose I restrict the diagonal function to be a quadratic function. That is more restricted. That means you restrict your candidate for diagonal function. So, in a sense, you restrict yourself. But the nice thing about it is you simplify the design problem. Okay, so that's always the pros and cons. Okay, that's when you put additional constraint on your structural Lyapunov function, but the thing you simplify your design. Okay. So what do we mean by quadratic Lyapunov function is as follows? That means I select the Lyapunov function candidate as a quadratic function of the state. Here the state means x. So if you see x transpose times x, then that's a quadratic. That means second order function. And here we added p as a positive definite matrix. So this could be a Lyapunov function candidate. And if you want this function, or this quadratic function, to guarantee stability, definitely you hope that the derivative of this Lyapunov function along the state trajectory, that means the time derivative of dx, is what? Less than 0 or become negative definite. So I could then take the derivative, time derivative of this vx. And if you take the time derivative, it becomes x transpose px dot plus x dot transpose px. So that you can see. So the first term, x transpose px dot, you could then substitute a plus b0 into that. You will then ask, should there be additional term? Yes, they should. Okay. Because our system, so there should be in the design of that term. But if you look at the stability property here, okay. But the stability property is the property a plus b0 h. Okay, so if you want to show stability, all you care about is this metric. So there should be a v1w term coming in, but that's not to your interest because you only think about stability. So definitely here, okay, we should, for example, a plus b0 plus b1w, but that's something that's not relevant to stability. So it's a bit neglected. And similarly, if we x dot transpose plus px, then you have this. And through arrangement, you will end up this kind of property. So suppose this particular function is less than 0, then the system will then be stable. And this P is a positive definite matrix. And this particular equation, again, contains unknown P and unknown F. Definitely one way to do it is for you can then assign a particular P. For example, you can assign P to identity, and then find the F whether that can be satisfied. That's possible, but that can be restricted. So therefore, we do not want to restrict P to a particular function at this stage. Rather, we just have this particular function, but we allow it to be any positive definite matrix. Okay, so we have ended up with this kind of equation. But the best thing about this, there's a coupling between P and F. So definitely you will hope that this one to be less than 0. Okay, because this is the necessary and sufficient condition for stability. And for this one to be less than 0, that means for this term to be negative definite, one sufficient condition, I could then add another term. Because this is a negative number. Then if I have this negative number, add something to this negative, then that's guaranteed, that's what. That means this will be a sufficient condition for that. Because this particular term, F transpose RF, will be greater than or equal to 0. Because R is a positive definite matrix. So this term will be greater than or equal to 0. So suppose this condition is satisfied. That's automatically guarantee this one. And this is necessary sufficient for stability. So if I can achieve this, then I could then achieve stability. Okay. And nice thing about this, and definitely you will see F and F here, but then we by completion of the square, then we end up this. So for this equation, I could then rewrite this equation as follows. So you could then see the F transpose RF here, F transpose RF, and you could see F transpose B zero transpose P equal with F transpose R inverse, so this will cancel and be zero transpose. And then also this term which is here. But then you add one additional term, so you have to subtract it. Okay, so that's essentially the same equation as this. So what's the benefit of this equation? The benefit of this equation is, in the original equation here, P and F, they are coupled. Okay, because you see P and F multiply together, same thing here. But now, suppose you look at this equation, definitely you can see P and F coupled there. But the nice thing about this equation is, you have one particular equation that's independent of F. So it has nothing to do with the feedback. And another equation, okay, it's a little complicated, but you could see that suppose I assign F equal to this term. That means I make this zero. And that's essentially what you want, because this particular term will be greater than equal to zero. And you hope this to be negative, definitely. So suppose you could suppress this, it will be better. That means suppose you can make it zero. That gives you more freedom to select P. Okay. So therefore, you could then select F, so that this term is zero and so it's better. So if I select this one, then this term will be zero. And then you end up this equation. So this regard in a sense is important, because in the original equation we see a coupling between P and F. But by relaxing a little bit, by adding a term actually, by using this sufficient condition, I end up this equation. So this design is sufficient. That means suppose you can solve P, solve this equation, and then design F accordingly. Then you can stabilize it. And for this particular equation, if you look at more closely, I will hope that P to be positive definite. And also this, if you look at this equation, you have P and P there, so that's a quadratic function of P. But if I multiply this particular equation by P inverse from left and right, can I do that? Yes, because P is positive. So P inverse over in this. So if I look, let X to be P inverse. Then in that case, the equation to be solved becomes this one. So it amount to one particular X, positive definite, and satisfy this equation. So this is LMI, that's the linear metric inequality. So if you are able to solve the linear metric inequality for X, then you are done, because then you then solve P and then you can find the control. So the design procedure is very straightforward. Okay? And this is possible because we have a state feedback. And definitely you will ask what this R is. Okay? By introducing R, what did you lose? Okay. That means you will then ask the difference between this and that. So add up there. So one thing you can think about, suppose this R to be very small. So the difference between these two seem to be very small. That means for R approach to zero. That's so, because all I need to do is R to be positive definite. Positive definite can be 100, can be 0.41, so it can be very small number. So as long as it's greater than zero, then you are okay. So suppose I have R many relatively small, then that's still okay. So that means although this is sufficient condition, but the margin between the two is controllable. I mean, you can adjust the margin by, for example, reducing R. So what's the implication of that? If we look at this controller there, definitely the R is arbitrary as long as positive. So you can then solve this equation. But one observation is as follows. That means suppose you make R to be small to make the difference between the two small. Then the controller F tend to be this R inverse. So So your gain will be increased. Okay, so that's something that you could observe. So typically, you will see an increase of the gain, and then that tend to stabilize the system. So that's why people sometimes you need a high gain for feedback. That's because of this trend. And indeed, if I increase the gain, it's possible to stabilize the system that's originally unstable. Okay. As long as you know how to do it. So with the above understanding, we'll definitely hope to extend the result quadratic stabilization to address robustness issue. So we'll talk about uncertainty, and definitely we'll define what we call matched and unmatched uncertainty. Essentially, we'll try to look at stabilization and robustness. So we're talking about robust stability now. So when we consider robustness, then think about uncertainty. So one way that we can model the uncertainty mention can be as follows. So the linear system is x dot equal to ax plus b0 u. But somehow, this metric A and this metric B0, they are subject to uncertainty, and the uncertainty can be delta A and delta B. Okay, so delta A and delta B stand for uncertainty. And suppose these two uncertainty satisfy this kind of constraint. Okay, so this is assumption. That means with this kind of constraint, that means delta A can be modeled as B0 multiplied by EA. Delta B can be modeled as B0 multiplied by EB. EA and EB are unknown. So EA, EB are known, but B0 is known to us. So the uncertainty in this sense is what? That means this uncertainty is constrained to be in a subspace of B0. Okay. So this, if you prefer, this is the uncertainty that we have briefly mentioned, although I didn't talk too much. We'll talk about the classification of uncertainty. Okay. There's a word that's about success constraint. Okay. So we sometimes we more the norm of the uncertainty is bounded to the norm constraint. But sometimes we have subspace constraint. That means this uncertainty will happen in a particular direction. That means around certain spaces. And this is an example of what we call subspace constraint. That means this particular uncertainty, delta A and delta B, have to be in the range space of B0. Okay. Although EA and EB are not known to me, but it's said to be range space of B0. Okay, so in the range space, so B0. And this kind of condition, one is said to us, sometimes we're given a name we call a matching condition. That means so-called match uncertainty. That means the uncertainty happens along the certain subspaces. Such matching condition. And this type of uncertainty is not unusual in a sense, because sometimes suppose the uncertainty happens in your input channel, and that can only get into the system along this particular direction. So that's not unusual in this kind of uncertainty. And definitely you will then ask, why do we bother by using a match and unmatched uncertainty? And typically, unmatched uncertainty means that this condition are not satisfied, okay, or any of this condition are not satisfied, matched. But the thing is, if you have matched uncertainty or you set a matching condition, it simplifies the design. So we'll look at this issue first and try to extend to unmatched uncertainty later on. Okay, with that assumption or this matched uncertainty, we need three additional assumptions. The first assumption may look old to you, but it's indeed made without loss of generator. here that we say the metric A is asymptotic stable. And another additional condition is uncertainty EA, which is CH3, that's bounded, and EV is bounded, and also EV is also additional bounded by 1. Okay. We'll comment on this. The first assumption is the metric A to be asymptotic stable. And if you remember, the objective here to have robust stabilization. That means you want to stabilize the system and with robustness. So can I make this assumption? The answer is yes. Why that? Because in your design, you can design this in 2 steps. The first step is assume that you don't care about the uncertainty first. And then all you care about is A, B, 0 is controllable. And in that case, you can then introduce a state feedback. Make this A plus B0 F. Yeah? So you could then stabilize this A. So this is net, we call it net without loss of generality. Because suppose original A is not stable, that's okay. And you can then apply a state feedback A plus B0 F stable. And then this is replaced by A plus B0 F. So this assumption can be made without loss of generality. And the second and third criterion is for, that means EA, actually this is the same, is bounded. Okay. So we don't care about what exactly EA is. All we care about, there exists a bound. And this particular bound is known to me. Okay. And definitely in certain control exercise, you may say, I don't know what EA is, but as long as it's bounded uncertainty, you're okay. So you could then start with a very large number, that's okay. And the third condition is a little bit tricky. That means, again, I will hope that EV to be, let's say, a certain bound, small EV, but this particular bound has to be strictly less than 1. Okay. And if you are sensitive now, that means if you read the lecture, read the textbook, then you will pay some attention to this one. Okay. Because this turns out to be very important criteria or assumption. Then you would then ask, why do I need this assumption? Okay. This assumption is needed because if you remember that we are having B0 plus delta E, and delta E equal to B0 E. So in this case, here we have B0 identity plus EB. Okay. So in our control input channel, we have a B0 and then this I plus whatever EB. This is the time. And why am I interested in bounding this one? Because suppose I violate this condition, there's a possibility that means ED plus I can be reversed sign. Okay, because suppose I violate this condition, it's possible that I plus ED can reverse the sign. You can then think about the scale case. And what's the consequence is that maybe originally you have a negative feedback, but all of a sudden it becomes positive feedback. And then that could destroy all the situation. That's something that we want to avoid. That's why this kind of constraint or this kind of assumption can to be met. And it turns out to be important. So with this kind of assumption, the first one is that without loss of generality. The third and second one is for us to understand there's certain bound exists for this uncertainty. And with this not too much assumption, we could then do a lot. Now if I consider the diagonal function, this again is a quadratic diagonal function, function for Px, then definitely we know it's a system is stable as long as this particular diagonal equation is satisfied for certain positive semi-definite or positive in Q. Okay, so if this equation is satisfied, then this can be the diagonal candidate. Okay. So we'll start with this equation and then we'll see how can we proceed. So since I have assumed metric A to be asymptotic stable, so I could do what? I could pick up Q, any Q that's a positive definite. identity being one particular example, but I could definitely have lots of choices. Then I could then solve this equation. So A is stable, so I can find the positive definite P. And I will then realize this particular function, or this quadratic function, is a diagonal function for the unperturbed system. That's mean when there are no uncertainty. This is a diagonal function. I will hope then that this particular function remains the diagonal function for the perturbed system. You see what I mean? This is related to the so-called diagonal stability. Remember the argument of diagonal stability, that means I have a system that's when system is unperturbed. I can come up with diagonal function. And I will hope to analyze how much tolerance I could have when there are uncertainty. And now, in a similar thinking, I'm using this particular equation, but I try to generalize this particular diagonal function so that's applicable to perturbed system. Okay. So to see this, then all you need to do is, suppose this is my diagonal candidate. Okay, all I need to do is to check the derivative of Vx to be less than 0. Okay, so I need to evaluate this term. And this particular term is here. Okay. And I just plug in x dot. And x dot, I have to go to here. That means x dot equal to this equation, so I could plug in this term there. And also, I could then assume the feedback is this manner. Where did this come from? This comes from the previous thinking. Essentially, similar stuff. Except that I'm using a small r here, that's a matrix, for simplification. Okay. And then you could then have a matrix here. But that's still okay. So I'm adopting this kind of control structure as we had talked about for quadratic stabilization, and I will hope that this particular diagonal function is still applicable. So if I look at this equation, then I will then end up this kind of expression. So you see a little bit complicated here, but that's essentially just by substituting this term in that. So I will hope what? I will hope this term to be less than 0. Okay, I will hope this term to be less than 0. Oh, but now, if I look at this equation, then it's a little bit complicated because it contains what? Contains EA, EB, which are unknown to me, because EA, EB are uncertainty. And it's also contains the EA product between EA and P being, although it's derived here, but still that's really complicated. But I can do this. First of all, Q being a positive definite metric, Q is always greater than minimum eigenvalue of Q multiplied by identity. And this greater than equal to is in the sense of positive semi-identity. Okay? So that's something else. And the second equation is also can also be taken care of. That means if you look at this term, and second, assume that the normal EV, let's say small EV, so I could then have this kind of expression. And for this term, I would then have this kind of result. That's mean this is a completional square, and then I could then adopt this condition. The derivation are straightforward, but you can then definitely go over this kind of derivation. But one important notice is that here I will hope this term to be less than 0. So for this, I look for its Q lower bound. I look for a lower bound of this term, but here I have to look for the upper bound because there's a positive sign, there's a negative sign, negative sign. So if you want to look for the sufficient condition, you will have to know which direction you will be looking for. That's mean here I have to look for the upper bound because I want it to be less than 0. I want to establish a sufficient condition for stability, or for robust stability. So I look for upper bound of this term, lower bound of this term, and lower bound of that term. So let's end up with this. And therefore, this particular term will be less than this boundary. Okay? And why is this important? Because originally you have a capital EA and capital EB, which are uncertainty. But now if you look at this bound, they are internal small or normalized EA and EB, which are assumed to be known to you. So this bound can be evaluated. That's when you can compute this bound. Okay, because EA and EB is known to you. And with that, we end up this kind of situation. So that means this is definitely a sufficient condition for that one. So that means Vx dot is less than this one. And definitely suppose this is less than 0, then you could then guarantee this one will be less than 0. So you are. And here we can do certain manipulation again, because there are certain terms, that's an S squared. And there are also certain terms has Px, x transpose P and then Px. Right? X transpose P and Px. Px, x transpose P. So I just will go into two groups. So for this one, x transpose x, this has x transpose x, so I just have the same term. And then this another term, let's have x transpose P and then Px. Okay? So you hope that this will be less than or equal to 0. Okay? So you hope that this term to be negative. You also hope this term, which term is to be negative as well. So that means the answer is, can you do it? And the answer definitely yes. That means suppose you already know EA and EB. So you can select Q so that the minimum eigenvalue of Q to be greater than this term. Select R so that R less than this term. Because Q and R here Q only has to be positive elements. R is a free variable you can select. R is any positive scale. So you could then select R and P freely. But if you want to achieve robust stability instead of stability, you can select Q and R in this manner. Then in that case, the system not only stable but also stable for all permissible beta and beta B. That means it's robust stability. Okay, so you achieve robust stability by appropriately selecting Q and R. And for this R, you can also realize the significance of EB to be less than 1. Okay? Because if the sign reverse, then you cannot find R, because R has to be positive. So that's why this 1 minus EB has to be positive. And this particular result is also interesting because remember here that in a sense we will hope the Q to be as large as possible, while R to be as small as possible. And if you go back to our control, suppose Q is large, P will be increased. P will be increased. R is small, R inverse will be increased, so you have a high gain. So you tend to have a gain that's very high. Suppose you want to achieve robust stability. And this sometimes is important in certain thinking, I think. But that's can be, can be understandable because if you want to control system so that's subject uncertainty will have not too much effect on it, then definitely you will hope that the control tend to be dominant. But this domination have to look at for the structure. That means this particular B0 and P have to be there. And then, but that's essentially the result of robust stability. So therefore, we could then conclude that it's always possible to stay bounded to match on uncertainty, provided that the state is accessible. This is a very important statement because it's had to be bounded because here we need EB to be the product less than 1. Match uncertainty because we assume this data A and data B to be in the range space of E0, and state is accessible because we rely on control by using state feedback, and this is a state feedback. And why is this statement is important? Because if you relate this, or this, then you may not be able to assure this kind of performance or this kind of robustity. And as an example, we can look at this. Okay. Now, suppose I have uncertainty A plus delta A and then B0 U. Then you could then use B0 plus delta E to make it more complicated. Just for illustrative purpose, we assume we have this kind of uncertainty. So uncertainty here, delta A is not necessary in the range space of B0. Rather, we assume delta A can be mono of this one. And this is one particular structure of uncertainty we have been assuming. That can be understandable. That means delta A can be contain several uncertainty there, and then each can be an element. So for example, this A can be a measure n by n. So you may have several entries, let's say uncertainty. And each entry, the position of each entry is specified by EI and FI. And the extent of uncertainty is governed by mu I. Okay, so this something, for example, in your homework, probably you also see similar arrangement. And here I'm assuming that mu I is unknown. But EI and FI is unknown because that's related to the position of uncertainty in A. Although mu I is unknown, but I assume that it's bounded by a certain variable. So that's a certain scalar, mu I bar. So this kind of uncertainty called unmatched because this delta A is not necessary in the range space of B0. Okay. So that's we call it unmatched. So definitely you will ask, suppose I have unmatched uncertainty. Can I do a similar thing? Because in the previous statement we have shown that if you have match uncertainty, you can do a lot of things because you can always stabilize it or stabilize the uncertainty or you have robust stability. But now suppose I relate it a little bit. That means suppose this remain bounded, okay, but if it unmatched, then what's going on? So that's something you can ask. So this is unmatched uncertainty. And definitely you hope you can then press a similar trick. That means assume F equal to this one. Here I'm using measure again, but you can then assume to be scalar, doesn't matter. So I assume this F has this kind of structure. That means the state feedback gain equal to minus R inverse B0 transpose P. And with this controller, if you substitute in it and then assume similar the outcome function, we end up with this. And how does this come from? This is coming from similar derivation we have for this kind of argument here. Okay, so in a sense you are adopting the same diagonal function candidate and evaluate the derivative. And the derivative definitely related to A transpose P, PA, and so forth. And that's the particular equation that you end up with. So this equation related to the derivative of the diagonal function, and definitely that depends on E and F. Okay, so you end up with this kind of expression. And for this kind of equation, definitely you will hope that you can then verify that one. But if you look at the result here, the result states that A robustly stabilizing statement again can be constructed, provided you can find the solution here. I think where P and Q satisfy this equation. And the proof of this result is for you to assume this diagonal function and then show the stability equal to this. And then suppose this equation is solvable, then you are done. So what's the difference? The difference is very important. The difference is for match uncertainty, okay, the equation, the Q and R can always be found. That means the controller can always be found. Okay, so the controller more or less guaranteed to exist as long as you satisfy this previous assumption there. But if you look at the result here, there is no saying about the existence of P and Q. That means if you can find this P to this equation for certain Q and R, then you can then use this one to stabilize it. But this particular equation is not guaranteed to exist. That means the solution to this equation is not guaranteed to exist. So this particular equation is not automatically solvable. That means sometimes if you are lucky, you can solve this particular P, but this equation may fail to be solved. Okay? So that's essentially the difference between a mesh and mesh condition. That means suppose you have mesh condition, the uncertainty can always be taken care of. That means you can always find the controller, stabilize the system robustly. But if you have a mesh uncertainty, even with state feedback, you may not be able to find a solution, or you may be able to find a controller that's robustly stabilized system. And that's important. That's because if you cannot find a controller that's state feedback controller that robustly stabilized the system, then there's no way also for you to have a powerful feedback controller to do the job. Okay? So that's fundamentally very important. So whether this particular equation is solvable, definitely it's many important implications for whether you can find the controller that robustly stabilize the system. So this particular equation definitely will be interesting to us. So what's the difference between this equation and the previous equation? In the previous equation, you will see also we have P and P here. Okay. But somehow through this arrangement, we could then separate that one. But here, unfortunately, we cannot do similar trick. Okay. And so this equation becomes a quadratic equation of P. And in the previous example, if you recall what we have said, here, definitely you have also P and P here. It's a similar structure, but somehow in this particular equation, you then realize there is no constant term. So you are okay because you are allowed to multiply by P inverse, so you end up this kind of equation. But, so you can compare it to this equation and, for example, this particular equation. So if you see this, there's a constant term there and constant Q there. Okay? And you may ask, suppose I make Q0, but the Q0 is not what you want because you want Q to be a little bit larger because you want Q to be larger than something. And also this is DC term, so you cannot multiply by P inverse. So you can see the slightly difference in certain assumption. You can then have a different kind of formulation, and then let's make a certain problem become more complicated. But the question that you would then ask is, suppose I'm facing this kind of equation. Okay. Can I solve that one? Or how do I solve it? Okay. And that's essentially the equation that we talk about. We call it algebraic equation. Then take a break, and after we come back, we'll talk about particularly algebraic equation. And it's worth mentioning that this particular equation belongs to the so-called algebraic equation. So definitely we'll look at whether the problem is solvable and how to find the solution. Okay. So we'll take a break and we'll come